got a particularly interesting request, that at the end of this lecture, that's at the end of this lecture, that we get a photo of the group. Yeah. And Angela, who's an extremely competent technical, is willing to organise that at the end of it. If we all go up the front, we will use his video camera in this situation of zero light and get some kind of photo. Now the other point, Bill.
Yes.
There's a limited time in some sense if we want to also have discussion.
Right.
Now, perhaps the discussion is not. Decidiamo, capito? Sono le 5, abbiamo detto che... When do we have to finish here? Dica. 6:30, secondo me al massimo 6:30.
Al massimo, va bene.
Capito? I mean, non compreso forse un po' di più, capito? I don't want to push because nothing's really... Va bene? Ok, cominciamo la terza lezione.
Difference. I was trying to, I feel very strongly that Grassmann's also makes up the G-men. Galileo, Grassmann wrote Grassmann's idea about equality and difference is certainly very intimately related. If we want to make a precise one-to-one correspondence, or something close, then there's a struggle to make that as clear as possible. So the nearly equal, the infinitesimals identified as the nearly equal, identified as the spaces where the pieces every piece has a unique point, and so forth and so on, seems to be a good start. What about the idea of the difference? Things being different. Well, I think, it means many things, obviously, but one sort of thing that it means is apples are different from pears. So you can have a lot of apples, which in one sense are different from each other, and a lot of pears, which in one sense are different. You know what are pears, right? I didn't say pears. But apples are different from pears. So, in other words, I was just thinking this morning, maybe this doesn't really make sense, but I wanted to say that the map is different. If when you go down to the components of the codomain, the pieces viewed as a space in its own right, the composite is a monomorphism. This kloof means it's a monomorphism. Well, it's we always have this problem with grammar, you see, when we talk about general concepts, but it is different, or X are different, you wouldn't quite want to say, but the idea is that the points in A are, this may be a bunch of fruit, you see, and you're mapping it into kinds of fruit, and you want them to be still. So it means, for example, to say that two global elements, are different. It says that they actually belong to different components. So I'm saying that the idea that 2 points can be not only naively different, but actually belong to different components, that is a reinforced form of difference. I was relaxing the idea of equality to have almost equal. By contrast, I'm strengthening the idea of difference to mean really completely different, i.e. different components. Well, so anyway, this is connected with another construction of extensive quality. Grossman correlated different with extensive, and intensive with equal. So the infinitesimals, obviously there's something intensive about them. That seems rather intuitive. What about extensive? Well, there's another quality, or in some cases here's an attempt, a very important attempt to construct another quality due to Hurewicz. There's a Hurewicz category associated to given category E. And what that is the objects are the same, the spaces in E, but it's actually a U enriched category. It's not just an abstract category. It's enriched over the same base that we had before. So the space of points of the maps between two things is the components of the function space. Assuming that the category E is Cartesian closed, but we also have this functor P lower shriek. Remember the usual, what we sort of intuitively think of as the arrows from X to Y, that's the set P lower star of the same function space. This should be a relatively familiar idea, but we can, instead of P lower star, we can apply P lower shriek, and we get a completely different U enriched category. We call the Hurewicz category. Now, why is it a category? You have to. This is one of the several places where the fact that P lower shriek preserves products comes in. Because you need composition for a category. Given any three objects, any three spaces, X, Y, and Z, you need to compose the elements of this so-called set of this Homestead. So this composition is defined starting from the strong composition that you always have in any Cartesian closed category. Whenever you have a Cartesian closed category, there's a canonical thing like that. So you apply the P lower shriek functor to this diagram. You have to be able to commute it with the cross in order to arrive at that, right?
Can you push it?
Oh, I'm sorry. I don't know, this seems to be the sort of thing that people working in lambda calculus never thought of. I don't know, it's obviously directly relevant to lambda calculus because, by the way, see this Hurewicz category is again Cartesian closed. In fact, in a very, very nice sense because the sums, products, and exponentials are the same ones that they were before. The same objects that the actual function space, the actual Cartesian product, and E, those objects still satisfy the same adjunction after you change this. This is a general feature about enriched categories and closed categories, but applied in particular in the Cartesian situation. This is again Cartesian closed. Again, a model of lambda calculus, in which if you have this P lower shriek operator, one model of lambda type lambda calculus, or even non-type, goes over into another. Not very good about this thing is that this is again, okay, I need another sheet. This functor little h, it's just the identity of objects, but it's the map from on each Hom set. It's just a map from points, which is E of x comma y, whatever you want to call it. In other words, the standard map from star to shriek, applied in particular to an exponential object, tells you how to map the Hom objects here. So this little h is called the homotopy type. So every space has its homotopy type, which is an object in this presumably simpler category. It's not that much simpler, but now technically this if E, I usually want E to be a topo. Actually, I've only so far. Well, I've mentioned the third axiom for cohesion, very much tied up with the value of the partial map classifier. But most of the construction just depends on Cartesian closure and extensivity. Extensivity and Cartesian closure are two distinct reasons why you have the distributive law of sums and products. Extensivity implies a distributive law. Cartesian closure implies a distributive law. But neither one of those implies the other. They're sort of two. A hiding algebra is Cartesian closed but not extensive. You know, in countable sets it's extensive but not Cartesian closed. There are there's sort of two different reasons for fundamental distributivity. But, so the thing is this, so there's an obvious functor here, which is just, well, again, represented by 1. For Ewig's category, the maps from 1 into something, well, that's a U-valued functor, of course. But notice what it is, it's actually the components of X. So what to this category seem to be the bare points, or the points, is what were the components, pieces originally. So you've taken these objects and you've defined new objects whose points were the old pieces. But it consists of much more than just points, because the figures of various shapes also survive. And of course, the idea in homotopy theory was the crucial kind of figure is a sphere. A sphere, not a ball, but a sphere. The surface of the circle, two-dimensional sphere, which is the surface of the three-dimensional ball, etc. That the meaning of the maps from each particular sphere into a given space Y, taken all together, somehow are a system of very profound invariants of the space, which come up in all kinds of analysis. Now, what I wanted to say was that this ought to be equality. You want homotopy to be a quality.